Hello, I'm Francisco Andrade. I'm with University of Waterloo. I'm part of the robotics team and to some extent the exoskeleton and wearable sensors team from Katia at the University of Waterloo. Today I want to talk to you about my little escapade into human studies. The title is Double Support Assessment of Human and Robot Work for Application in Low Friction Environments, or the way I want to think about it, how to let robots enjoy Canada. So, why double support? Well, when we have contact with single and double support is kind of easy. You have the acceleration of the center of mass, just one contact. As long as you ensure that you are inside the friction cone, you will not slip. And that's easy to determine if you are with just one contact, right? But when you have double support, the actual distribution of the forces is non-deterministic, so you can have infinite solutions. So that makes it kind of hard. And robots at the current moment struggle with walking on ice, especially bipeds. If anyone knows of any biped walking on ice, I'll be very happy to know about it. I've seen a little humanoid skate, but that's not the same thing. So they struggle. And what can we do to help them? I know that humans can walk on ice, so how do they do it? More specifically, the research question that I have right now is, how does the force distribution in double support compares between the human and a typical robot walk? We're here that typical robot walk is courtesy of power robotics. What and when are the maximum coefficients of friction during a normal walk for both human with different materials touching the ground and how they compare to the robot values? And lastly, how can we use this information to improve or evaluate robot walking? So I took a look at what the statement says about double supporting human studies. I was very surprised to see that very few addressed what is the type of contact they have with the environment. They don't even mention if they're wearing shoes or barefoot. The one that I've seen being used more common, specifically for the double support division or distribution, was called the smooth transition algorithm. Although algorithm might be kind of a stretch of a word, it's more like an heuristic. What they do is basically they have these two functions that basically they're exponentials with a fixed coefficient, and they use the one on top for anterior to posterior motion, which in my case is going to be the x direction. And this one for everything else, all the other parts of the contact range. So yeah, and they scale these values by the immediate value just before you start double support. I saw that there was later an improvement of this when they used this kind of single function, but they extrapolated the coefficient and they made the coefficient depending on different variables. One of them is the maximum value of the forces, the slope between the two forces, the two values just before they start double support, the base velocity, the force value just before they start double support, the duration of the double support. And each coefficient has a very kind of unique formula, and they look more or less like this. So this is the coefficient for just that value on x. What I found interesting and valuable is that they have information not only from the single axis, but also from the vertical axis, which is very convenient for considering coefficient of friction. So I took these two algorithms and collected a little bit of data. We collected 9 subjects, 5 trials each, with each of them with a different type of contact surface. So we have barefoot, shoes, and socks. As you can see here, this is representative. I asked them to take the first step on the first property with the right, the second with the left. And I took also samples from the robot side. The 3 speeds that I set, which is basically just a twist and a rostopic, are 2, 1.5, and 1. I collected 4 experiments for each. The robot has a rubber sole, and I use the FT sensors to collect the information. So from the human side, this is what I saw. The first column of each axis is the inter-subject variation. So what was the mean among all the subjects and how they variate with respect to that. Then I have like the STA algorithm and improved STA. And for me, if the value obtained by this algorithm is lower than the inter-subject variation, I would consider it kind of good. So what I was able to observe is on the x-axis, yes, the STA remains kind of lower under the inter-subject variation, except for the shoes. The STA was not good. For the z-axis, I can see that the STA remained lower than the inter-subject variation for all of them, which is good. The STA was decently good, but again, above. For the y-axis, it was all pretty bad. As a note, the comparison with what they report in their respective papers was 10% error for x, 6 for x, 20, 18, 5.6, and 2.8, which is not what I got. Just to take a little look at how this actually looks like, this is the z-axis. You can see that the STA, which is the red line, kind of overestimates and underestimates, so bad fit. The improved SDA overestimates in the beginning, but there's kind of a good fit towards the end. On the x-axis, the SDA has a very bad estimation, it overshoots pretty badly. The other one has a more or less tracking, let's say not great, but more or less. For the y-axis, it's just bad. So the SDA is very easy to use, but it's inaccurate. And the improved SDA can be kind of good for x and z, but not y. Now, I also took a look at what the coefficients of friction would say. I found that the shoes are very different from socks and barefoot. The high peak, the row profile looks kind of simpler compared to that rich profile from the human. For the x-axis, we have the peak for the shoes on the landing foot. For the robot is actually on y, on the trailing foot. So the key points that I want to leave you with is there's a clear distinction between barefoot socks and shoes in terms of the humans. The shoes require or use a high coefficient of friction on the landing foot and have a wider basing on the second part of the trailing foot. There's a need to consider different force distribution based on contact, and the state of the art doesn't seem to account for this. Improved SDA seems to be a decent approach, not considering the y-axis. The y-axis requires a different approach, and rubber on ice is actually 0.15, and all humans and robots would go above this threshold. Or another way to say it would be, when on ice you want to walk, what you wear matters a lot to describe level support. Improved SDA might do the work if you squint your eyes a lot, and to the size you use it not. If completely unaware, on the floor you will end, because no matter human or robot, friction goes above the ice constraint. Stay sharp.
So we have three minutes sharp-ish.
Yes.
So you're looking for other examples. It's probably not exactly what you're looking for, but I know that Aaron Ames has approved in a planer walker, and they put oil on a treadmill, which I don't know how that affects the treadmill, but that's an example for you.
I'll go to the later to write it down.
Yeah.
Yes.
When you were testing the subjects in shoes, were they wearing a standardized shoe or was it their own that they came in?
Yeah, when I was in the poster session, they asked me that too. I didn't even think about it. So my first time in human studies, that was a great thing to do next time. And no, actually I got one of the subjects from with snow boots. And no. Yeah.
I know that Vibram has, I've seen this, I don't know whether they've released it or not, but I've seen them at their factory, they had, maybe I'm getting in trouble now, but they have these like crazy soles that like normal all over ice, but using those soles help with robot and human walking in that case?
Probably yes, like changing the interface with the environment, that's something that specifically works on ice. Definitely would work, but that also means that I'm either changing permanently the shoe of the robot or the foot of the robot, or just the sole, which might be something to look at. But I also want to use this to improve the walking of the robot. So I want to use this information as well. Okay, thank you everybody.